For this video, we will be discussing several calculations involving buffer solutions. For our first sample exercise, we have this problem. What is the pH of a buffer that is 0.12 molars in lactic acid and 0.10 molars in sodium lactate? For lactic acid, the acid dissociation constant is 1.4 times 10 raised to negative 4. For this problem, we are asked to calculate the pH of a buffer containing lactic acid and its conjugate base, which is the lactate ion. We will first determine the pH using the method described in the common ion effect, and that is to identify the major species in the solution. And for this problem, our major species are lactic acid, sodium ion, and the lactate ion. So the lactic acid lactate ion conjugate acid-base pair determines the concentration of hydrogen ions and thus pH. So we must write the equilibrium reaction describing this, which is shown in the slide. And then after that, we set up our ICE table or the ICE table, which stands for the initial, change, and equilibrium concentrations. And then we input the concentrations into the ICE table. So we have already filled up our ICE table, and then now we can set up our equilibrium constant expression. And from our ICE table, we will be getting the equilibrium concentrations and substitute it into the expression. So we will be getting this. And then we solve for the hydrogen ion concentration, or our X, which is 1.7 times 10 raised to negative 4. So here you can see that Ka is small and a common ion is present. So we expect our X, or our hydrogen ion concentration, to be small relative to either the initial concentration of our lactic acid, which is 0.12 molars, or the initial concentration of our sodium lactate, which is 0.10 molars. So thus, we can further simplify our expression or our equation to give us this. So now we can calculate for our pH. So our pH is 3.77. Calculating the pH when the Henderson-Hasselbalch equation may not be accurate. So in the previous slide, we have used the Henderson-Hasselbalch equation, and we have also applied the principle of the common ion effect. So there are two ways in solving for the pH of buffer solutions, but the usual route that we choose is by using the Henderson-Hasselbalch equation because it is much more simplified. But there are scenarios wherein the Henderson-Hasselbalch equation is not applicable. And so we have this problem. Calculate the pH of a buffer that initially contains 1.00 times 10 raised to negative 3 molars of acetic acid and 1.00 times 10 raised to negative 4 molars of sodium acetate in the following two ways. So we are asked to calculate it using two ways. The first is by using the Henderson-Hasselbalch equation, and the second one is by making no assumptions about the quantities. So that means we will need to use the quadratic equation. So the Ka for acetic acid is given, which is 1.80 times 10 raised to negative 5. For this problem, we are asked to calculate the pH of a buffer in two different ways. So we know the initial concentrations of the weak acid and its conjugate base and the Ka of the weak acid. So first, we will be using the Henderson-Hasselbalch equation, which relates the pKa and ratio of acid-base concentrations to the pH. Then we will redo the calculation, making no assumptions about any quantities, which means that we will need to write out the initial change and equilibrium concentrations as we have done before. And in addition, we will need to solve for quantities using the quadratic equation since we cannot make assumptions about the unknown being small. So first, we set up our Henderson-Hasselbalch equation. And then we know that for pKa is equivalent to negative log of Ka. So for pKa, we already have our value, which is 4.74. So therefore, we can just simply substitute the concentrations that were in the given, assuming that they are equilibrium concentrations and assuming that X is negligible and X is small. So therefore, for the first way, by using the Henderson-Hasselbalch equation, our pH is equals to 3.74. Now, for the second task, we will be redoing the calculation without making any assumptions. So just like in the common ion effect, we will first identify the major species and then set up the equilibrium reaction, the I stable, and then the equilibrium constant expression. Okay, so this is our equilibrium reaction. This is our I stable, and this is our equilibrium constant expression. Now that we have set this up already, let us substitute the values to the equilibrium constant expression. Okay, so after substituting, so we will not be assuming that X is too small and X is negligible. So because of that, we will be having this quadratic equation. So we will be applying the quadratic formula. And I hope that you still remember how to use the quadratic formula because it will still be very useful. And with that, we can calculate for X. So our X is equals to 8.76 times 10 raised to negative 5. And that will be our hydrogen ion concentration. So therefore, pH is equals to 4.06. Now that is for the second part of calculating for pH for this problem. Now here, I have took a screenshot photos of our first process and the second process. The first process is by using the Henderson-Hasselbalch equation to calculate for the pH. Well, the second one is by calculating the pH using the common ion effect route without making any assumptions. Now, if you will notice, for the first part, our calculated pH is 3.74. Now, without making any assumptions, without neglecting the value of X, and without assuming that X is too small, we have calculated pH as 4.06. So if you notice, there is a difference in the calculated pH. So always remember that the simplifying assumption only works because the concentrations of the acid-base conjugate pair are both 1,000 times larger than Ka. Remember that our Ka is 1.8 times 10 raised to negative 5. However, in this sample, the acid-base conjugate pair concentrations are only 10 to 100 as large as Ka. So the initial concentration of our acetic acid is 1.0 times 10 raised to negative 3, while that of the acetate ion or the sodium acetate is 1.0 times 10 raised to negative 4. So therefore, we cannot assume that X is small compared to the initial concentrations. So the best answer for this is the pH is 4.06. So therefore, we see that the assumptions behind the Henderson-Hasselbalch equation are not valid when the initial concentrations of the weak acid or the weak base is small compared to its Ka or Kb. So that is how we are going to determine whether we will be using the Henderson-Hasselbalch equation or whether we are going to make assumptions or not. So I hope you learned something from this video and I hope that you can apply it in your calculations.